In this assignment, you'll be building two data types. The first is percolation. This is going to be a data type that solves the so-called percolation problem, which we'll be describing in a moment. You will also build a percolation stats data type that is going to use your percolation data type to learn something interesting about math. Okay? So let's first talk about the percolation problem. And I'm going to do this by running this visualizer. So after you've written percolation.java, this visualizer will work. And what does it do? Well, if I click somewhere in this space, we'll see white squares appear. And so what you should imagine is happening here is that when I click, I'm digging out squares of the Earth, right? This is a solid universe with tons of rock. And when I click, I'm digging out space. Okay, so, all right, I've dug a big chamber. We could live in here safely from all the dangers of the outside world. So this right here you should think about as the top of the world, and this is the core of the world. And so something interesting will happen if we dig a square out that touches the top. Notice it is blue. This blue represents the fact that there's some kind of ocean up here that, let's say, that whenever you dig a hole, the water will flow in. And so if I were to dig something like that, all of this fills up, and so forth. So if I keep digging, click here, it again flows all the way up, and it defies gravity because there's just so much pressure and it fills all of this space. Okay? So that's going to be one of the main tasks you do. But really, the punchline is going to be related to this. See where it says does not percolate? This world doesn't percolate. What does that mean? Well, as soon as you get to a situation where there exists a path from the ocean to the core of the world, the system will be said to percolate. Okay, so now it says percolates. That's just saying that water can actually reach the middle. So the data type you're going to build, you're not going to build the GUI. You're going to build this percolation class. So what does it do? Well, when you create a percolation object, it's a n by n grid. That's what n means. When you say open, that's saying dig out a square of the Earth. When you say is open, that's asking whether or not that space has been excavated. So this is a space that's open. We will also have a method that you have to support called is full, which means that has water reached it from the top? All of these squares, everything in blue is full, but this square is not full, right? Because of the fact that no water has reached it, okay? And I guess I should also say these squares are all open, right? They're open in the sense that they've been dug out, but they're also full. Okay, so it's open for water, and water has reached it. And then you'll also have this handy little method, number of open sites, which will tell you how many sites are open. And then finally, the most interesting one is the percolates method, which tells you whether or not the system percolates. And that tells you whether or not there exists a path from the top to the bottom. Finally, there is a main method. Now, depending on where you're taking this class, you may or may not actually have to do this unit testing, so make sure you consult the spec at the institution at which you are taking this class. So, you might ask, what is the point of this percolation project exactly? Like, I get that it's a cool metaphor for digging out under the earth and water and all that, but I don't quite get it. Well, you're right to question that, and it turns out there is a little more to that. And it's going to have to do with the fact that we're going to use this percolation data type as the engine that drives this percolation stats simulator. So let me talk a little bit about theoretical percolation here. So you can imagine generating random worlds with different openness probabilities. So here I've generated a world where every square has a 40% chance of being open. This is relatively non-porous rock, you can imagine, right? And it turns out that if you run a bunch of simulations, you will see that a world with 40% open spaces, that it almost never percolates. In other words, there's no path from the top down to the very bottom. By contrast, if I set that openness probability to say 80%, then almost any world you generate is going to percolate, right? I mean, we can see that there's gaps here, but the liquid in this case is able to easily get around it. And in the middle, somewhere around, say, 60% openness chance, well, you might generate a world, and sometimes it doesn't percolate. Here, the water wasn't able to get down to the bottom, but in this world, it was. So these both have 60% open spaces. This is one which doesn't reach all the way to the bottom. This one does. Okay. Now, what's interesting, and what has been observed, is that, okay, well, it's no surprise that if you have more open spaces, you're more likely to percolate, have a path from top to bottom. But what is not obvious, and needs a little bit of theoretical treatment, is that you can actually measure what is the chance that a world percolates for a given openness, okay? So at 40% openness, somewhere around here actually, at the 40% openness level, there's almost no random worlds that percolate. So even though it looks like we're kind of close to percolating each of these cases, if you just keep generating random worlds with 40% openness, there's just no path from top to bottom, right? And if you're at, say, 80%, almost every single world you generate is going to be percolating. There'll be a path from top to bottom. And surprisingly, at the 0.593 level, there's like a sharp change, right? Somehow we go from worlds in which there is no percolation to worlds where there's percolation with a very small change in parameter. And so this is evocative of things like, you might have heard of the notion of a finely tuned universe, that there's like the fine structure constant, the weak nuclear force strength, those kind of things. If any of those parameters were just a little different, then you might have a world in which there are only black holes, or in which there was never fusion in the first place, so there were no stars, and there was just eternal darkness. And any of those little changes can make a big difference. So if we relate this to the world that we live in, you and I, this P star might be something about the porosity of the Earth, right? I mean, this is just a crude model. But in this world, where there's no percolation, that means that if you dig into the ground, you can't reach, say, underground oil reservoirs, because everything is locked up. But in this world, there's easy oil. You dig in, you get all of this gushing black goo that you can use to power your civilization, and hopefully not drive yourself into extinction through climate change. Okay, so that's the advantage over here. You get access to all that energy. And so what is the value of P star? P star is the value, by the way, at which this change happens. So theory predicts that such a P star should exist, and that's a mathematical thing. But the only known way to actually calculate the value of P star is with a simulation, and that's what we're setting out to do in this assignment.